All right, well, let's look at another example with the integral test. But before we do that, I want to quickly mention the way that we wrote down the theorem before was a little bit more restricted than it needed to be. It turns out the function only needs to be decreasing for x greater than or equal to 1 and continuous for x greater than or equal to 1, because those are the only values that we're actually taking into account when we're evaluating the integral. In fact, in a minute, we're going to relax that restriction even further. But to see why we need that, let's look at the example. All right, so let's look at the sum from n equals 1 to infinity of log n over n. All right, and we'd like to determine if that converges or diverges. And it's fairly straightforward to convince yourself that some of the techniques we've seen earlier, such as the nth term test, the geometric series, and telescoping series will not be applicable here. But just to make sure, let's actually try them. So recall the nth term test says that if the limit as n goes to infinity of a to the n is not equal to 0, then we know that it diverges. So let's take this limit. And notice that looks like the form infinity over infinity if we plug in, since large arguments of a log make the log large. And so that's indeterminate. We can't tell what the answer is yet. But when you have infinity over infinity, one of the techniques you can use is L'Hopital's rule. And L'Hopital's rule says that you can take the derivative of the top, which would be 1 over n, and the derivative of the bottom, which would be 1, and evaluate that limit instead. And as long as that exists, we'll get the same answer. All right, again, that only applies when we have infinity over infinity. And this limit is much easier. Notice the top is going to approach 0, and the denominator is 1, and so this is 0. Okay, so the nth term test is going to be inconclusive here because it only tells us about divergence if we get something other than 0. So that doesn't help us. Geometric series, if you recall, that applies when we have terms that are constants raised to some power. Clearly that's not applicable here. And then telescoping series came into play when we had usually a difference involved in our individual terms. And again, there's no subtraction here, and it doesn't look like there's any clever ways to recast that form so that we do get subtraction and cancellation from consecutive terms. So this is not geometric. It's not telescoping. And so therefore, we're out of luck based on those approaches. But we would like to try the integral test. And before we can do that, there were 3 stipulations. We needed the function to be positive, decreasing, and continuous. And previously, we said those needed to be true for values of x that are greater than or equal to 1. And so let's actually graph that function out. I've got Desmos up. And so here's what the graph of log x over x looks like. And you'll notice that it reaches a peak value around that looks like E, 2.718, and it's decreasing and positive and continuous after that. But before that point, it is not decreasing, it's actually increasing. And so technically, as we've stated the integral test, it cannot be applied to this problem. However, the goal is to test for convergence or divergence. And if you think about the area under the curve, the area before this point is definitely finite, right? There's no way that you can have an area with width about 2 and height less than 1 and get an infinite area out of that. So the divergence or convergence of the integral is going to depend on the tail. What happens for the large arguments? And the same thing would apply if we had a series. Right, so let me actually sketch what a series might look like. So we could plot y values that are less than or equal to, if we call this f of x, if we plug in the values of x rounded down, we'll get a series. All right, and so there's a bunch of rectangles there. You notice the first couple of rectangles are getting taller, but after that, it looks like the rectangles are getting shorter. And if we change our y scale, that becomes a little bit clearer. So let's maybe go from -1 to 1. All right, so now you can see that a little bit better. the rectangles are getting shorter in the long run. It's just those first couple of rectangles where the order doesn't match up. But if we're trying to tell if the series converges or diverges, notice that the first two rectangles or three rectangles don't matter. They can't make it go to infinity. Ultimately, if there's an infinite amount of area there, it's got to come from the tail end. And so our integral test can be modified slightly. We can actually apply it to any series starting with any value of n. And so let's say that we start with n equals some number k. Well, as long as the function is decreasing and continuous above that k, and the integral above that k converges, then we can conclude that the series converges. And likewise, if the integral diverges, the sum diverges as well. Okay, so the integral test is a little more flexible than it was stated originally, and it's a little more flexible than it's stated in your textbook, as long as the function is decreasing, positive, and continuous eventually, meaning for sufficiently large inputs. And let me actually bring up the revised form of the theorem so you can see it. All right, there we go. That looks a little better. All right, so I've revised our theorem so that we have a k in terms of the lower value where it must be decreasing and continuous. And I've started my sum at k and my integral at k in the statement as well. So we've revised it so that it's a little more flexible now. If the sum from k to infinity is what we're interested in, then the integral from k to infinity is a value sufficient comparison. All right, so let's see if we can apply this result, this more flexible version of the integral test to this problem. So the log of n over n is not decreasing, but if we look at our picture again, notice it looks like from 3 on, we could certainly compare. Because from 3 to infinity, the function is decreasing, positive, and continuous. So these two things, the sum from 3 to infinity and the integral from 3 to infinity, must do the same thing. And so let's evaluate that integral from 3 to infinity. I'll use a u substitution for that. We'll let u equal log x, and du would therefore be 1 over x dx. And we'll want to change our limits. When x is equal to 3, u is equal to the log of 3. And as x goes to infinity, u is going to approach infinity as well, right? If you take the log of larger and larger numbers, you get larger and larger numbers going off to infinity. And so this integral can be written as the integral from log 3 to infinity of u times 1 over x dx, which is just du. And so that integral can now be written as, well, the antiderivative of u would be u squared over 2. And we want to go from log 3 to infinity. And if we plug in, we will have infinity squared over 2 minus log 3 squared over 2, which is definitely got to be divergent. All right. So if the sum from 3 to, or if the integral from 3 to infinity of log x over x diverges, we can conclude that the sum from n equals 3 to infinity of log n over n must diverge. Well, and if that sum diverges, then of course adding 2 extra terms, well, that's not going to change anything, right? Adding 2 finite terms is not going to change whether it diverges. It will still diverge with those missing terms. So, moral of the story here is the integral test, I'll scroll back up here, applies more generally. As long as the function is positive, decreasing, and continuous eventually, then you could compare the sum and the integral, and they will do the same thing.